Picture this. You're standing on a beach watching the sunset when suddenly a column of fire tears through the sky above you. The ground beneath your feet trembles. The air itself seems to split apart with a thunderous roar that rattles your bones. And riding atop that pillar of flame is a massive metal cylinder weighing millions of pounds, accelerating from 0 to over 17,000 miles per hour in just 8.5 minutes. How does a rocket go into space? How is that even possible? I mean, think about it for a second. We live at the bottom of an invisible ocean of air that's pressing down on us with the weight of 14.5 pounds per square inch. Above that, there's nothing but the cold vacuum of space stretching for billions of miles in every direction. No air to breathe, no ground to walk on, just emptiness so complete that sound itself cannot exist there. And yet, somehow, we've figured out how to build machines that can climb out of this gravitational well we call home and soar into that void. We've created metal beasts that can carry humans, satellites, and space stations beyond the reach of Earth's atmosphere. But the physics behind how this actually works, most people have absolutely no clue. I hope you had a wonderful day today, and I am really glad to have you here. If you find comfort in these gentle explorations of our natural world, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let me take care of the rest. There's absolutely no problem if you drift off during this exploration. Before we begin our ascent, I'd love to know where you're listening from tonight. Feel free to comment your time and location below. Also, I might warn you, this video might be a little too interesting to fall asleep to and not watch till the end. You might want to apologize me for that in advance. Let's begin. Here's what's crazy. The basic principle that launches rockets into space is the same one that makes you stumble backward when you jump off a boat. It's Newton's third law of motion, and it's been staring us in the face for over 300 years. But the engineering required to actually make it work, that's where things get mind-bendingly complex. See, getting to space isn't just about going up. It's about going really, really far sideways. And to understand why, you need to grasp something that will completely change how you think about what astronauts are actually doing up there. They're not floating in zero gravity because they're far from Earth. They're falling toward our planet every single second of every single day. They just happen to be moving so fast horizontally that they keep missing it. I know that sounds impossible, but by the end of this video, you're going to understand exactly how we've mastered the art of controlled falling. You'll discover why rocket fuel makes up over 90% of a rocket's weight at launch. You'll learn about the invisible forces trying to tear these machines apart as they climb toward the stars. And you'll see why getting to space is actually the easy part compared to what comes next. But here's what nobody talks about. The story of how rockets work isn't just about physics and engineering. It's about humanity's refusal to accept limitations. It's about taking one of the most hostile environments imaginable and finding a way to not just survive there, but to thrive. Because when you really understand how we get to space, you realize we're not just launching rockets, we're launching pieces of human consciousness into the cosmos itself. What I'm about to show you isn't just the textbook explanation of how rockets work. Once you see how this actually works, you'll never look at a rocket launch the same way again. Because what we're really watching isn't just a machine climbing into the sky. We're watching humanity break the most basic rule of existence on our planet. We're watching something born of Earth escape Earth entirely. So let's start with the most basic question. What exactly is a rocket fighting against as it tries to reach space? First, there's gravity. Not the gentle tug you feel when you drop your phone, but a relentless force that's pulling down on every single atom of the rocket with over 6 million pounds of force. That's like having 40 blue whales sitting on top of your spacecraft, constantly trying to drag it back to the ground. And gravity doesn't get tired. It doesn't take breaks. It's working against you every single second from launch until you finally escape Earth's influence completely. But gravity is just the beginning. As soon as that rocket starts moving, it crashes into something else that wants to destroy it. Air resistance. Now, you might think air is pretty much nothing, but when you're trying to push a building-sized object through it at thousands of miles per hour, air becomes like concrete. The atmosphere doesn't want to get out of the way. It pushes back with tremendous force, heating the rocket's surface to temperatures that would melt steel, trying to rip apart anything that dares to challenge its dominance. And then there's the most dangerous enemy of all: physics itself. Because here's the thing about getting to space: you can't just point a rocket straight up and gun it. That's not how orbital mechanics works. To stay in space, you need to be moving sideways at over 17,000 miles per hour, not up. Sideways. Fast enough that when gravity pulls you toward Earth, you've moved so far horizontally that you've curved around the planet instead of hitting it. This is where most people's understanding of space travel completely falls apart. They imagine astronauts floating around in zero gravity because they're far from Earth's gravitational pull. Wrong. The International Space Station is only about 250 miles above our heads. If you could drive straight up at highway speeds, you'd reach the space station in about 4 hours. Gravity up there is still about 90% as strong as it is down here. So why are astronauts floating? Because they're in a state of constant free fall. They're falling toward Earth at exactly the same rate as their spacecraft, which means, relative to their surroundings, they feel weightless. But they never actually hit the ground because they're moving sideways so fast that Earth's surface curves away beneath them faster than they can fall toward it. Think about it like this: if you threw a baseball really, really hard, it would travel in an arc and eventually hit the ground. But if you could somehow throw that baseball at 17,000 miles per hour, the arc of its path would match the curve of the Earth. It would fall around the planet forever, never hitting the ground. That's exactly what's happening with every object in orbit. But achieving that 17,000 mile per hour sideways velocity, that's where rockets come in. And the physics of how they actually work is way more brutal than most people realize. See, rockets work on a principle that seems almost too simple to be true. They throw mass in one direction really, really fast, and Newton's third law pushes them in the opposite direction. Action and reaction. Push down, go up. It's the same physics that happen when you fire a gun and feel the recoil, or when you blow up a balloon and let it go. But here's where it gets complicated. Unlike a car that can grip the road or a plane that can push against the air, a rocket has nothing to push against except itself. It has to carry everything it needs to create thrust. The fuel, the oxidizer, the engines, the structure to hold it all together. And because of something called the rocket equation, this creates a vicious cycle that makes getting to space incredibly difficult. The rocket equation is probably the most important formula in all of space travel, and it's also the reason why rockets look the way they do. Basically, it says that to go faster, you need more fuel. But more fuel makes you heavier, which means you need even more fuel to accelerate that extra weight, which makes you even heavier, which means you need even more fuel. You can see how this spirals out of control pretty quickly. This is why the Saturn V rocket that took humans to the moon weighed 6.5 million pounds when it sat on the launch pad, but the command module that actually returned to Earth weighed only About £12,000. Over 99% of that massive rocket was fuel and structure that got thrown away during the flight. We're basically building throwaway skyscrapers just to get a small capsule to the moon and back. And that fuel isn't just gasoline like you put in your car. Rocket fuel has to work in the vacuum of space, where there's no oxygen to support combustion. So rockets carry their own oxidizer, usually liquid oxygen, which weighs even more than the fuel itself. The space shuttle's main engines burned liquid hydrogen and liquid oxygen at a rate of over 1,500 gallons per second. That's like emptying a swimming pool every few minutes, just to create the thrust needed to escape Earth's gravity. But even with all that fuel, rockets can't just light their engines and blast straight up to space. The path they take is actually a carefully choreographed dance with physics that has to be executed with split-second precision. During the first few seconds after launch, the rocket does go mostly straight up. This is to get through the thickest part of Earth's atmosphere as quickly as possible. Because remember, air resistance is trying to destroy the vehicle. The faster you can climb above the dense lower atmosphere, the less energy you waste fighting against air that doesn't want to move out of your way. But as the rocket gains altitude and the air gets thinner, something interesting happens. The flight path starts to curve. This is called the gravity turn, and it's one of the most elegant maneuvers in all of engineering. The rocket starts tipping over, gradually pointing more and more toward the horizon instead of straight up. This might seem counterintuitive. Why would you point away from space when you're trying to get to space? Because remember, getting to space isn't about altitude. It's about speed, specifically horizontal speed. The gravity turn allows the rocket to start building up that crucial sideways velocity while still climbing high enough to escape the atmosphere. The timing of this turn is absolutely critical. Turn too early, and you waste energy fighting through thick air while traveling horizontally. Turn too late, and you end up going straight up with no horizontal velocity, which means you'll just fall straight back down. The computers controlling modern rockets are constantly calculating the optimal flight path, adjusting the trajectory hundreds of times per second based on wind conditions, engine performance, and 1,000 other variables. But here's where things get really interesting. As the rocket burns fuel and gets lighter, it starts accelerating faster and faster. This is because the engines are producing the same amount of thrust, but they're pushing against less mass. It's like the difference between pushing an empty shopping cart versus a full one. The empty cart accelerates much more quickly with the same amount of force. This acceleration continues to build throughout the flight, and by the time the rocket reaches space, the astronauts inside are experiencing forces that would crush an untrained person. They're being pushed into their seats with 3 or 4 times their normal body weight, fighting just to breathe as their spacecraft climbs toward the stars. And we haven't even talked about staging yet. This is where rocket design gets truly ingenious. Since rockets have to carry all their fuel with them, and since most of that fuel gets burned in the first few minutes of flight, engineers realized they could make rockets more efficient by throwing away the empty fuel tanks as they go. This is why most rockets are built in multiple stages. The first stage contains the massive engines needed to lift the entire rocket off the ground and accelerate it through the thick lower atmosphere. Once that fuel is exhausted, the entire first stage gets jettisoned, and a smaller second stage takes over. This second stage doesn't need to be as powerful because it's now pushing a much lighter payload, and it's operating in the thin upper atmosphere where air resistance is minimal. Some rockets have 3 stages, with each one optimized for different parts of the flight. It's like climbing a mountain and throwing away your heavy winter gear as you ascend to higher, warmer altitudes. You only carry what you need for each part of the journey. But staging creates its own engineering challenges. Those stages have to separate cleanly at exactly the right moment, often while traveling at thousands of miles per hour and experiencing tremendous forces. The connections between stages have to be strong enough to hold together during launch, but also designed to break apart instantly when commanded. And the upper stage engines have to ignite perfectly, even in the harsh environment of space where there's no air pressure and temperatures swing between hundreds of degrees above and below zero. The precision required for all of this to work is almost beyond comprehension. We're talking about timing events to fractions of a second while traveling at speeds that would cross your entire city in minutes. A delay of just a few seconds in stage separation, or an engine that doesn't ignite properly, can turn a successful mission into a very expensive fireworks display. And that's just the beginning. Because once you finally reach space, once you've overcome gravity and air resistance and successfully navigated the staging sequence, you're faced with an entirely new set of challenges. You're now in an environment where the normal rules of physics that we're used to on Earth no longer apply. There's no up or down, no air to breathe or sound to hear, just the endless vacuum of space and the complex orbital mechanics that govern how objects move in this alien realm. But we're getting ahead of ourselves. Before we can understand what happens once you reach space, we need to dive deeper into exactly how those rocket engines create the tremendous thrust needed to escape Earth's gravitational grip. Because the science behind rocket propulsion is far more complex and fascinating than simply burning fuel and pointing the exhaust downward. The heart of a rocket engine is where chemistry becomes raw power, where controlled explosions happen thousands of times per second to create forces that can literally bend steel. And when I say controlled explosions, I'm not talking about the gentle combustion in your car's engine. I'm talking about reactions so violent, so intense, that they create temperatures exceeding 5,000 degrees Fahrenheit and pressures that would crush a submarine. Let's start with the most common type of rocket engine, the liquid-fueled engine. These monsters work by mixing two chemicals that really want to react with each other. Usually, that's a fuel like rocket-grade kerosene or liquid hydrogen, and an oxidizer like liquid oxygen. When these chemicals meet in the combustion chamber, they don't just burn. They detonate in a continuous controlled explosion that creates expanding gases moving at incredible speeds. But here's what's truly mind-blowing about this process. The temperatures inside a rocket engine's combustion chamber are hot enough to melt copper, hot enough to vaporize steel, hot enough to turn almost any material known to humanity into plasma. So how does the engine not destroy itself in the first few seconds of operation? The answer is one of the most elegant solutions in all of engineering. The walls of the combustion chamber and the rocket nozzle are hollow, with thousands of tiny tubes running through them. Supercold fuel is pumped through these tubes before it reaches the combustion chamber, which cools the engine walls and prevents them from melting. It's like air conditioning for a device that's literally containing the power of a continuous explosion. This cooling system is so effective that the inside of the engine can be hot enough to melt tungsten, while the outside remains cool enough to touch with your bare hand. We're talking about temperature gradients so extreme they seem to violate common sense. The engineering precision required to make this work is absolutely staggering. Now, the fuel and oxidizer don't just casually flow into the combustion chamber. They're forced in by pumps that are themselves marvels of engineering. These aren't the little pumps you might find in your basement. These are turbo pumps that spin at over 30,000 revolutions per minute while handling fluids at pressures that would make your head explode. Literally. The main fuel pump on a space shuttle engine, for example, produces more horsepower than all the engines in a Formula One race combined, and it has to do this while pumping liquid hydrogen that's been cooled to -400 degrees Fahrenheit. The material science required to build pumps that can handle these extreme conditions without failing is absolutely incredible. But pumping the fuel is only half the battle. The real magic happens in the combustion chamber and nozzle design. You see, when those chemicals react, they create hot gases that want to expand in all directions. The job of the rocket nozzle is to channel all that expanding gas in one specific direction to create thrust. This is where the shape of the nozzle becomes critically important. Rocket nozzles aren't just tubes. They're carefully designed with a narrow throat that accelerates the gas to supersonic speeds, followed by an expanding bell shape that continues to accelerate the exhaust even faster. By the time those gases exit the nozzle, they're moving at speeds that would make a bullet look like it's standing still. The math behind nozzle design is incredibly complex, involving fluid dynamics equations that would make your head spin. Engineers have to account for how the gas pressure and temperature change as it flows through the nozzle, how the expanding gases interact with the nozzle walls, and how to optimize the shape for maximum efficiency at different altitudes. Here's where it gets really interesting. A rocket nozzle that's perfectly optimized for sea level performance will actually lose efficiency once the rocket reaches the thin upper atmosphere. This is because the nozzle design depends on the outside air pressure to work properly. At sea level, atmospheric pressure helps squeeze the exhaust gases as they exit the nozzle. But in the vacuum of space, there's no outside pressure to provide that squeezing effect. This is why some rockets use different engine designs for different parts of their flight. The first stage engines are optimized for sea level performance, with shorter nozzles that work efficiently in thick atmosphere. But the upper stage engines have much longer, wider nozzles that are designed to work in the vacuum of space, where there's no atmospheric pressure to worry about. Some rocket engines can even adjust their nozzle shape during flight. These are called aerospike engines, and they're like having a nozzle that automatically optimizes itself for any altitude. The technology is incredible, but it's also incredibly complex and expensive, which is why most rockets still use simpler fixed nozzle designs. Now, all of this combustion and gas expansion creates thrust according to Newton's third law, but the amount of thrust depends on two main factors. First is the mass flow rate, which is simply how much exhaust mass the engine throws out per second. Second is the exhaust velocity, which is how fast that mass is moving when it leaves the nozzle. The relationship between these factors is captured in a simple equation. Thrust equals mass flow rate times exhaust velocity. But here's the catch. To get more thrust, you can either throw out more mass per second or throw out the same mass at higher speed. And it turns out that throwing mass faster is much more efficient than throwing more mass. This is why rocket engineers are obsessed with exhaust velocity. The faster you can accelerate your exhaust gases, the more efficient your engine becomes. And this is where different types of rocket fuel really start to matter. Liquid hydrogen and liquid oxygen create one of the fastest exhaust velocities possible with chemical rockets. When these two chemicals react, they produce water vapor as exhaust, and water molecules are relatively light. Light molecules can be accelerated to higher speeds more easily than heavy molecules, which means higher exhaust velocity and more efficient engines. But liquid hydrogen comes with its own problems. It has to be kept at incredibly low temperatures. It takes up enormous amounts of space, and it tends to leak through the tiniest gaps in fuel tanks. Many rocket designers prefer to use rocket-grade kerosene and liquid oxygen instead, even though the exhaust velocity is lower, because kerosene is much easier to handle and store. And solid rocket motors work on completely different principles. Instead of mixing liquid chemicals in a combustion chamber, they burn a solid propellant that looks like a giant chunk of rubber packed with explosive chemicals. The space shuttle's solid rocket boosters, for example, contained over 1 million pounds of this solid propellant each. The advantage of solid rockets is simplicity. No complex pumps, no cryogenic fuel handling, no intricate cooling systems. You just light them and they burn until all the fuel is consumed. But the disadvantage is that once you light a solid rocket, you can't turn it off. It's going to burn until it runs out of fuel, whether you want it to or not. This makes solid rockets perfect for applications where you need massive amounts of thrust for a short period of time, like getting a heavy rocket off the launch pad. But they're terrible for fine adjustments or precision maneuvers in space, where you need to be able to start and stop your engines on command. The thrust-to-weight ratio of an engine determines whether a rocket can even lift off the ground. If your engines don't produce more thrust than the total weight of your rocket, you're not going anywhere. This seems obvious, but it creates some interesting design constraints. Heavy payloads require bigger rockets with more powerful engines. But bigger engines are heavier, which means you need even more thrust to lift the extra engine weight. It's another one of those vicious cycles that makes rocket design so challenging. Every component you add to increase performance also adds weight that decreases performance. This is why rocket engines are some of the most power-dense machines humans have ever built. A single space shuttle main engine weighs about 7,000 pounds, but produces over 400,000 pounds of thrust. That's a thrust-to-weight ratio of almost 60:1. For comparison, a high-performance sports car engine might have a power-to-weight ratio of 3 or 4:1. But raw power isn't everything. Rocket engines also have to be incredibly reliable, because there's no room for error when you're strapped to millions of pounds of explosive fuel traveling at thousands of miles per hour. Every component has to work perfectly, every time, under conditions that would destroy most machines in seconds. The development process for a new rocket engine takes years and costs hundreds of millions of dollars. Engineers build and test hundreds of different versions, each one slightly different from the last, trying to optimize performance while maintaining reliability. They test these engines under every conceivable condition, firing them again and again, until they understand exactly how they'll behave in flight. Even with all this testing, rocket engines are still pushed to their absolute limits every time they're used. The forces, temperatures, and pressures involved are so extreme that engines often can't be reused. They're basically controlled bombs that we ride into space, and the fact that they work as reliably as they do is a testament to the incredible skill of the engineers who design them. But engines are only part of the story. The fuel tanks that hold all those explosive chemicals, the guidance systems that keep the rocket pointed in the right direction, the structural elements that hold everything together under tremendous stress. Every single component of a rocket has to work perfectly in an environment that's actively trying to destroy it. The fuel tanks themselves are engineering marvels. They have to be strong enough to contain liquids under high pressure, while being as light as possible to minimize the weight penalty. Some rocket fuel tanks are so thin that you could poke a hole through them with a screwdriver, yet they can withstand the forces of launch and the thermal stresses of spaceflight. Cryogenic fuel tanks face even greater challenges. Liquid hydrogen is stored at -400 degrees Fahrenheit, while the outside of the tank might be baking in direct sunlight at hundreds of degrees above zero. The thermal expansion and contraction from these temperature swings would crack most materials, but rocket tanks are designed to flex and bend without failing. The guidance systems that control a rocket's flight path are perhaps even more impressive than the engines themselves. These computers have to process information from dozens of sensors hundreds of times per second, constantly calculating the optimal trajectory while accounting for wind, engine performance variations, and fuel consumption rates. Modern rockets can adjust their flight path by gimbaling their engines, which means physically tilting the entire engine to redirect the thrust vector. The precision required for this is incredible. We're talking about making adjustments measured in fractions of a degree while the engine is producing hundreds of thousands of pounds of thrust. Some rockets use small thruster motors for attitude control instead of gimbaling the main engines. These reaction control systems use tiny rockets that fire in short bursts to nudge the spacecraft in the desired direction. It's like parallel parking a building-sized object while traveling at thousands of miles per hour. The structural loads on a rocket during launch are unlike anything most people can imagine. The acceleration forces trying to compress the rocket from bottom to top. The aerodynamic forces trying to bend it sideways. The vibrations from the engines that can literally shake components apart if they're not properly designed. Rocket structures have to be simultaneously incredibly strong and incredibly light. Engineers use advanced materials like carbon fiber composites and specialized aluminum alloys to achieve strength-to-weight ratios that seem impossible. The entire structure flexes and bends during flight like a giant spring, but it's designed to flex in specific ways that don't compromise the integrity of the vehicle. All of these systems, engines, fuel tanks, guidance computers, structural elements, have to work together in perfect harmony for just a few minutes to accomplish something that defies our everyday experience of physics. They have to accelerate millions of pounds of rocket from a dead stop to over 17,000 miles per hour while climbing through 100 miles of atmosphere and executing a complex trajectory that would make a fighter pilot dizzy. And here's what's really remarkable. Despite all this complexity, despite the extreme forces and temperatures and the thousands of things that could go wrong, modern rockets succeed in reaching space over 95% of the time. We've gotten so good at this impossible task that we almost take it for granted, but reaching space is just the beginning of the journey. Once a rocket escapes Earth's atmosphere and achieves orbital velocity, it enters a realm where the normal rules of motion no longer apply. A realm where objects can travel for years without any propulsion, where tiny adjustments can result in massive changes in trajectory, and where the dance between spacecraft and celestial mechanics becomes a delicate ballet performed across the vast emptiness of space. The transition from powered flight to orbital mechanics marks a fundamental shift in how spacecraft move and navigate. During the rocket-powered ascent, thrust overcomes gravity through brute force. But once in orbit, spacecraft must work with gravity rather than against it, using the subtle interplay of velocity and gravitational attraction to maintain their path around Earth. This is where the physics of orbital mechanics becomes truly mind-bending. Once you're traveling at that magic 17,000 miles per hour, something extraordinary happens. You're no longer fighting gravity, you're dancing with it. Gravity becomes your partner instead of your enemy, constantly pulling you toward Earth but never quite catching you because you're moving sideways too fast. But here's what most people don't realize about orbital mechanics. It's completely counterintuitive. Everything you think you know about how objects should move gets turned upside down once you're in orbit. Want to catch up to a spacecraft that's ahead of you? You don't speed up. You slow down. Want to slow down? You fire your engines forward, not backward. Want to change your orbit to a higher altitude? You have to speed up, but only at exactly the right moment, or you'll end up in the wrong place entirely. This is because orbits aren't just circular paths around Earth. They're ellipses, and the mathematics governing elliptical motion follow rules that seem to mock common sense. When you fire your engines to speed up, You raise the altitude of your orbit on the opposite side of Earth. Fire your engines at the wrong time, and instead of reaching your target, you might end up in a completely different orbit that takes you nowhere near where you wanted to go. The precision required for orbital rendezvous makes landing a plane on an aircraft carrier look like child's play. Imagine trying to meet up with a friend who's riding a motorcycle around a racetrack at 200 miles per hour, except the track is 250 miles above the ground, and you're also on a motorcycle traveling at slightly different speed. Oh, and you only get one chance to time your approach perfectly, because if you miss, you might not get another opportunity for several orbits. This is exactly what happens every time a cargo ship docks with the International Space Station. Both vehicles are screaming around Earth at over 17,000 miles per hour, and they have to match their velocities and positions with such precision that they can gently bump into each other like two butterflies landing on the same flower. The slightest miscalculation could result in a catastrophic collision that destroys both spacecraft. The computers controlling these orbital maneuvers are constantly solving equations that would take human mathematicians hours to complete. They're tracking the positions and velocities of multiple objects moving in three-dimensional space while accounting for Earth's gravitational field, atmospheric drag, and even the tiny gravitational influences of the Moon and Sun. It's like playing three-dimensional chess while riding a roller coaster in the dark. But orbital mechanics gets even stranger when you consider what happens if something goes wrong. On Earth, if your car breaks down, you pull over and stop. In space, there's no such thing as pulling over. There's no such thing as stopping. If your engines fail, you don't just sit there. You keep moving in whatever trajectory you were on when the failure occurred, potentially for years or even decades. This is why space missions require backup plans for backup plans. Every possible failure mode has to be considered and prepared for, because in space, you can't just call for roadside assistance. If something breaks, you have to fix it with whatever tools and spare parts you happen to bring with you. And if you can't fix it, you have to find a way to complete your mission anyway. The environmental challenges of space make Earth's most extreme conditions look comfortable by comparison. In direct sunlight, temperatures can exceed 300 degrees Fahrenheit. In Earth's shadow, they plummet to minus 250 degrees. These temperature swings happen every 90 minutes as spacecraft orbit in and out of Earth's shadow, causing constant thermal expansion and contraction that would crack most materials. There's also the radiation. Without Earth's protective magnetic field and atmosphere, spacecraft are bombarded by high-energy particles from the sun and deep space. This radiation can damage electronics, degrade solar panels, and pose serious health risks to astronauts. Spacecraft have to be shielded against radiation exposure, but shielding adds weight, and we're back to that fundamental challenge of rocket design where everything has to be as light as possible. The vacuum of space creates its own set of problems. Materials that are perfectly stable on Earth can outgas in vacuum, releasing chemicals that can contaminate sensitive instruments or cloud optical surfaces. Lubricants evaporate, seals fail. Even the human body starts to behave differently in the absence of atmospheric pressure. Micrometeorite impacts are another constant threat. Space might seem empty, but it's actually filled with tiny particles traveling at speeds that would make bullets look sluggish. A paint fleck traveling at orbital velocity hits with the force of a small bomb. Larger debris can punch holes through spacecraft hulls or destroy critical components. This is why spacecraft design is as much about survival as it is about performance. Every system has to be redundant. Every critical component has multiple backups. Mission planners spend years thinking through failure scenarios that most people would never consider, because in space, even the smallest oversight can be fatal. The International Space Station, for example, has been hit by debris thousands of times during its decades in orbit. Most impacts are too small to cause serious damage, but the station's hull is constantly being peppered by tiny particles that gradually wear away the outer surfaces. The station has to be periodically boosted to a higher orbit because atmospheric drag, even at that altitude, is slowly pulling it back toward Earth. Atmospheric drag might seem impossible at 250 miles above Earth's surface, but the atmosphere doesn't just stop at some arbitrary altitude. It gradually thins out over hundreds of miles, and even the incredibly thin air at the space station's altitude creates enough resistance to slow down objects over time. Without periodic reboosts, the space station would eventually spiral back into the atmosphere and burn up. This brings us to one of the most elegant aspects of orbital mechanics. The same atmospheric drag that threatens spacecraft can also be used as a tool. When missions to other planets need to slow down upon arrival, they often use a technique called aerobraking. Instead of burning fuel to decelerate, spacecraft deliberately dip into the planet's atmosphere, using atmospheric friction to slow down gradually over multiple orbits. It's an incredibly delicate process. Dip too deep into the atmosphere, and the spacecraft burns up like a meteor. Stay too high, and the drag isn't enough to change the orbit significantly. Mission planners have to thread the needle perfectly, calculating atmospheric density and spacecraft heating loads to within narrow margins of error. The Mars missions have perfected this technique over decades of practice. Spacecraft arriving at Mars often have highly elliptical orbits that take them far from the planet at their highest point and deep into the atmosphere at their lowest point. Each atmospheric pass removes a little bit of energy from the orbit, gradually circularizing it into the desired final orbit for science operations. But aerobraking isn't just about fuel savings, it's about precision. Chemical rockets are powerful, but they're also somewhat crude instruments for delicate orbital adjustments. Atmospheric drag provides a gentle, continuous force that can sculpt orbits with incredible precision over time. It's like the difference between using a sledgehammer and a scalpel. The mathematics governing all of these orbital mechanics trace back to Johannes Kepler's laws of planetary motion, formulated over 400 years ago. Kepler figured out that planets move in elliptical orbits by studying the motion of Mars with nothing more than careful observations and brilliant mathematical insight. His laws still govern every spacecraft we send into space today, but applying Kepler's laws to modern spaceflight requires computational power that Kepler could never have imagined. Mission planners use supercomputers to calculate trajectories that take spacecraft on multi-year journeys to distant planets, using gravitational assists from multiple worlds to achieve the velocities needed for interplanetary travel. These gravitational assist maneuvers are perhaps the most elegant demonstrations of orbital mechanics in action. By carefully timing a spacecraft's approach to a planet, mission planners can use the planet's gravity to accelerate the spacecraft, essentially stealing a tiny bit of the planet's orbital energy. It's like a cosmic slingshot that can add thousands of miles per hour to a spacecraft's velocity without burning a drop of fuel. The Voyager missions are the classic example of gravitational assist mastery. Both spacecraft used Jupiter's gravity to accelerate towards Saturn, then used Saturn's gravity to reach Uranus and Neptune. Without these gravitational assists, the missions would have been impossible with the rocket technology available in the 1970s. The spacecraft borrowed energy from the giant planets themselves to reach the outer solar system. But gravitational assists require planning trajectories years or even decades in advance. The planets have to be in exactly the right positions for the mathematics to work out. Mission planners call this planetary alignment, and it doesn't happen very often. The Grand Tour trajectory that enabled the Voyager missions only occurs once every 175 years. This is why space missions often seem to launch in clusters. When the orbital mechanics are favorable for reaching Mars, for example, multiple space agencies launch their missions during the same launch window. Miss that window, and you might have to wait 2 years for the next opportunity when Earth and Mars are properly aligned. The complexity of these calculations is staggering. Modern mission planning software can model the gravitational influences of every major body in the solar system, predicting spacecraft trajectories with accuracy measured in meters across distances of billions of miles. The precision is so incredible that mission planners can predict exactly when and where a spacecraft will be years in advance. But even with all this computational power, space missions still require constant monitoring and course corrections. The real universe isn't quite as predictable as our mathematical models suggest. Solar radiation pressure, variations in planetary gravitational fields, and countless other tiny perturbations can gradually nudge spacecraft off their intended trajectories. This is where deep space navigation becomes an art as much as a science. Navigation teams use radio signals to track spacecraft positions with incredible precision, measuring tiny Doppler shifts in radio frequency to determine velocity changes as small as a few millimeters per second. They can detect when a spacecraft's trajectory has drifted by just a few meters across distances of millions of miles. Course corrections in deep space require a completely different approach than launch operations. Instead of the massive thrust needed to escape Earth's gravity, spacecraft use small thrusters that produce just a few pounds of force. These tiny engines might fire for hours or even days to make gentle adjustments to the trajectory. It's like steering an oil tanker with a kayak paddle, requiring patience and precise timing. The fuel for these course corrections has to last for years or even decades, which creates its own engineering challenges. The thruster systems have to be incredibly reliable, able to fire on command after years of dormancy in the harsh environment of space. The fuel itself has to remain stable and usable across temperature swings and radiation exposure that would degrade most chemicals. Some spacecraft use ion propulsion systems that can operate continuously for years while consuming incredibly small amounts of fuel. These engines work by accelerating individual atoms to extremely high velocities using electric fields. The thrust is almost imperceptible, less than the weight of a piece of paper resting on your hand. But over months and years, this gentle push can change a spacecraft's velocity by thousands of miles per hour. Ion engines represent a completely different philosophy of space propulsion. Instead of brute force chemical rockets that burn intensely for minutes, ion engines provide whisper-quiet thrust that continues for years. They're perfect for deep space missions where fuel efficiency matters more than raw power. The Dawn mission used ion propulsion to visit 2 different asteroids, something that would have been impossible with chemical rockets. The spacecraft spiraled slowly away from one asteroid and gradually spiraled in toward another, using its ion engines to reshape its orbit over the course of years. It was like watching a cosmic ballet performed in slow motion across the vast emptiness of space. But regardless of the propulsion system used, all spacecraft face the fundamental challenge of operating in an environment that's completely alien to human experience. Every system, every component, every line of code has to work perfectly in conditions that exist nowhere else in our daily lives. The computers controlling spacecraft have to function reliably for years or decades, while being bombarded by radiation that would crash most consumer electronics in hours. The software has to be absolutely bug-free, because there's no way to send a technician to fix problems. Every possible scenario has to be anticipated and programmed in advance. Communication with deep space missions creates its own set of challenges. Radio signals travel at the speed of light, which seems fast until you're trying to control a spacecraft that's billions of miles away. Commands sent to spacecraft in the outer solar system can take hours to arrive, and confirmation that the commands were received takes hours more to get back to Earth. This means that deep space spacecraft have to be essentially autonomous, capable of making decisions without waiting for instructions from Earth. They have to be programmed with enough intelligence to recognize problems and respond appropriately, sometimes choosing between conflicting priorities without human guidance. The psychological challenges of these long-duration missions extend to the human operators as well. Mission teams might work on a single spacecraft for decades, watching it slowly make its way across the solar system. They become emotionally attached to these mechanical explorers, celebrating their successes and mourning their failures like family members. When the Cassini mission ended, with the spacecraft diving into Saturn's atmosphere, mission control erupted in both celebration and tears. They had guided this robotic explorer for 13 years, watching it revolutionize our understanding of Saturn and its moons. Its final plunge was both a scientific triumph and an emotional farewell to a mechanical friend that had traveled billions of miles to show us wonders we never could have imagined. This human element of space exploration often gets overlooked in discussions of rockets and orbital mechanics. But behind every successful mission are teams of engineers, scientists, and technicians who dedicate years or decades of their lives to these endeavors. They solve problems that have never been solved before, often working with incomplete information under tremendous pressure. The recent success of commercial space companies has brought new approaches to these age-old challenges. Companies like SpaceX have revolutionized rocket design by making their boosters reusable, dramatically reducing the cost of getting to space. Instead of throwing away multi-million-dollar rocket stages after one use, these stages now land back on Earth and can be flown again. Reusability changes the entire economics of space access. When rocket flights become routine and relatively inexpensive, it opens up possibilities that were never feasible before. Satellite constellations with thousands of spacecraft become economically viable. Space manufacturing and tourism start to look realistic. Even Mars colonization shifts from science fiction to engineering challenge. But reusability also creates new technical challenges. Rocket engines have to be designed to withstand multiple flights instead of just one. Landing systems have to work perfectly every time because a failed landing destroys the entire vehicle. The precision required to land a rocket booster on a platform the size of a football field after traveling hundreds of miles at supersonic speeds is absolutely incredible. The guidance systems for these landing maneuvers make the original moon landing look simple by comparison. The rocket has to flip around in mid-flight, reignite engines that have been shut down for minutes, and execute a controlled descent while compensating for winds and engine performance variations. All of this happens automatically, controlled by computers that make thousands of calculations per second. These technological advances are enabling a new era of space exploration where the fundamental question is shifting from "can we get there?" to "what should we do once we arrive?" The basic physics of rocket propulsion haven't changed, but our mastery of those physics has reached levels that would have seemed impossible just decades ago. We're now planning missions that would have been pure fantasy in the early days of space exploration. Missions to collect samples from asteroids and return them to Earth. Missions to land on comets and drill into their surfaces. Missions to send spacecraft to other star systems, journeys that will take decades to complete, but will give us our first close-up look at worlds orbiting distant suns. The principles we've explored, Newton's laws, orbital mechanics, the rocket equation, remain as fundamental as ever. But our application of these principles has become so sophisticated that we can now contemplate adventures that stretch human presence across the solar system and eventually to the stars themselves. The same physics that power a simple firework now enable us to dream of becoming a truly spacefaring civilization. The engineering marvel that makes all of this possible starts with something most people never think about. The moment that rocket lifts off the pad, it's not just fighting against gravity and air resistance. It's fighting against time itself. See, every second that passes during launch is a second where fuel is being consumed at an absolutely staggering rate. The Saturn V moon rocket burned through nearly 20 tons of fuel every single second during its first stage burn. That's like emptying a large swimming pool of rocket fuel every minute, just to keep the vehicle accelerating upward. But here's where the physics gets really interesting. As that fuel burns away, the rocket doesn't just get lighter, it gets exponentially more efficient. This creates what engineers call the acceleration curve, and it's one of the most beautiful demonstrations of physics in action you'll ever see. During the first few seconds of launch, when the rocket is heaviest, the acceleration is gentle. The massive vehicle slowly lifts off the pad, almost majestically, like it's defying gravity through sheer determination. But as fuel burns away and the rocket sheds weight, that same engine thrust starts accelerating a lighter and lighter vehicle. The rocket doesn't just speed up, it speeds up at an increasing rate. By the time the first stage engines shut down, the astronauts inside are being pressed into their seats with forces that would make a fighter pilot dizzy. They're experiencing 3, 4, sometimes 5 times their normal body weight, all while traveling at speeds that would carry them across entire states in minutes. This acceleration profile has to be carefully managed throughout the flight. Too much acceleration too quickly, and you'll crush the crew or damage sensitive equipment. Too little acceleration, and you waste precious fuel fighting gravity for longer than necessary. Modern rockets use computer-controlled throttling systems that constantly adjust engine power to keep the acceleration within acceptable limits. But managing acceleration is just one piece of a much larger puzzle. Because while the rocket is climbing through the atmosphere, it's also dealing with something called max Q, the point of maximum dynamic pressure. This is the moment during ascent when the combination of air density and vehicle velocity creates the highest aerodynamic forces on the rocket structure. Max Q typically occurs about 60 to 90 seconds after launch, when the rocket is still climbing through the thick lower atmosphere, but has accelerated to supersonic speeds. At this moment, the air resistance trying to tear the rocket apart reaches its peak intensity. The entire vehicle is being buffeted by forces that would rip apart most aircraft, while simultaneously being pushed upward by millions of pounds of thrust from below. The timing of max Q is critical for mission success. If the rocket structure isn't strong enough to handle these forces, the vehicle can literally break apart under the aerodynamic stress. But if the rocket is built too strong, it becomes too heavy to reach orbit efficiently. It's a delicate balance that requires incredibly precise engineering calculations. Some rockets actually throttle back their engines during max Q to reduce the stress on the vehicle. It seems counterintuitive to reduce power when you're trying to escape Earth's gravity, but it's better to take a few extra seconds reaching space than to have your rocket disintegrate in the atmosphere. As the rocket climbs higher and the atmosphere gets thinner, something remarkable happens. The air resistance that was trying to destroy the vehicle suddenly disappears. Above about 50 miles altitude, the atmosphere becomes so thin that aerodynamic forces become negligible. The rocket transitions from fighting through air, like swimming through molasses, to gliding through vacuum, like moving through empty space. This transition marks a fundamental shift in how the rocket behaves. Below 50 miles, aerodynamics dominates everything. The shape of the rocket, the fairings that protect the payload, even the way the vehicle is painted can affect its performance. Above 50 miles, aerodynamics becomes irrelevant, and only the raw physics of thrust and gravity matter. But reaching the edge of space is still not the same as reaching orbit. This is where many people's understanding of space travel breaks down completely. They think that once you get high enough, you're automatically in space and can just float around. Nothing could be further from the truth. Altitude is only half the equation for reaching orbit. The other half is velocity, and it's by far the more difficult half to achieve. Getting to an altitude of 100 miles requires about 10% of the energy needed to reach orbit. The other 90% goes into building up that crucial horizontal velocity of 17,000 miles per hour. This is why rockets don't just go straight up and then level off. The trajectory they follow is a carefully calculated curve that balances the need to escape the atmosphere quickly with the need to build up horizontal velocity efficiently. The flight path starts nearly vertical to punch through the thick lower atmosphere, then gradually curves over toward the horizon as the air gets thinner. The mathematics governing this trajectory are incredibly complex. Engineers have to account for how Earth's rotation affects the flight path, how winds at different altitudes will push the rocket off course, how the rocket's changing mass affects its acceleration, and dozens of other variables that can influence the final orbit. Earth's rotation actually provides a significant boost to rocket launches, but only if you launch in the right direction. Our planet spins from west to east at over 1,000 miles per hour at the equator. Launch your rocket toward the east, and you get that 1,000 mile per hour head start for free. Launch toward the west, and you have to overcome that rotational velocity, making your rocket work much harder to reach the same final speed. This is why most launch sites are located as close to the equator as possible, and why rockets almost always launch toward the east. Cape Canaveral in Florida was chosen as NASA's primary launch site, partly because it's relatively far south and has clear ocean to the east, where spent rocket stages can safely fall. The timing of orbital launches has to account for where you want to end up in space. If you're trying to rendezvous with the International Space Station, you can't just launch whenever you feel like it. You have to wait for the precise moment when your launch trajectory will intersect with the station's orbital path. These launch windows might only be a few minutes long, and if you miss them, you might have to wait days for the next opportunity. Launch window calculations involve tracking the motion of targets in space, while accounting for Earth's rotation, the rocket's flight time, and the complex orbital mechanics that govern how objects move once they reach space. It's like trying to hit a moving target with an arrow while you're also moving, and both you and the target are on a spinning platform. The precision required for these calculations is absolutely mind-boggling. Mission planners can predict exactly where a spacecraft will be in its orbit months or years in advance, accurate to within a few miles across distances of hundreds of thousands of miles. The mathematics involved would make your head spin, but the computers handling these calculations process them as routine number crunching. Once a rocket finally reaches orbit, the entire nature of the mission changes. During the powered ascent phase, success depends on engines working perfectly and structures holding together under extreme stress. But in orbit, Success depends on understanding and working with the subtle forces that govern how objects move in space. Orbital mechanics operates according to rules that seem to defy common sense. Speed up, and you actually end up going slower in the long run. Slow down, and you can end up going faster. Fire your engines in the wrong direction, and instead of going where you want to go, you end up somewhere completely different. This counterintuitive behavior comes from the fact that orbits are ellipses, not circles. When you change your velocity at one point in an elliptical orbit, you change the shape of the entire orbit. Speed up at the bottom of your orbit, and you raise the top of your orbit. Slow down at the top, and you lower the bottom. The effects of any maneuver don't become apparent until you complete a significant portion of your orbital path. Spacecraft navigation in orbit requires thinking in 3 dimensions across timescales that extend for hours or days. A maneuver you make now might not achieve its intended effect until several orbits later. Mission controllers have to plan sequences of burns that unfold over days or weeks, each one precisely timed to achieve the desired final orbit. The fuel requirements for orbital maneuvers are surprisingly small compared to the massive amounts needed to reach orbit in the first place. Once you're moving at orbital velocity, small changes in speed can result in large changes in orbit shape. A velocity change of just a few dozen miles per hour can alter a spacecraft's orbit by hundreds of miles. This efficiency makes possible some of the most elegant maneuvers in all of space exploration. Spacecraft can spiral gradually from one orbit to another, using tiny engine burns spread over weeks or months. They can use the gravitational influence of the Moon to change their Earth orbit without using any fuel at all. They can even use atmospheric drag as a tool for precise orbit adjustment. But orbital mechanics also creates some unique challenges. In orbit, there's no such thing as taking the direct route to your destination. The fastest way to get from point A to point B might involve going in completely the wrong direction first, then using orbital mechanics to curve around to where you actually want to go. Rendezvous operations, like docking with the space station, require a completely different mindset than any form of transportation on Earth. You can't just point toward your target and accelerate. You have to think about how your orbital velocity will change as you get closer, how the gravitational forces will affect your trajectory, and how to time your approach so that you arrive at exactly the right place at exactly the right time. The International Space Station orbits Earth once every 90 minutes, traveling at over 17,000 miles per hour. A cargo ship trying to dock with the station has to match not just the station's position, but also its velocity vector precisely. The relative velocity between the two vehicles at the moment of contact has to be just a few inches per second, or the collision could destroy both spacecraft. This precision is achieved through a series of carefully planned orbital maneuvers that bring the cargo ship gradually closer to the station over the course of several days. Each maneuver is designed to adjust one aspect of the rendezvous, whether it's changing the orbital plane, adjusting the timing, or fine-tuning the final approach velocity. The computers controlling these maneuvers are constantly solving equations that describe the motion of objects in Earth's gravitational field. They're tracking positions and velocities with incredible precision, while accounting for factors like atmospheric drag, gravitational perturbations from the Moon and Sun, and even the tiny effects of solar radiation pressure on large spacecraft surfaces. But even with all this computational power, human operators remain essential for orbital operations. The real world is more complex than any mathematical model, and unexpected situations arise that require creative problem solving. When systems fail or conditions change, Human ingenuity often makes the difference between mission success and failure. The recent development of reusable rockets has added another layer of complexity to orbital mechanics. Not only do mission controllers have to get the payload to orbit successfully, but they also have to bring the rocket booster back to Earth for a controlled landing. This requires solving two completely different trajectory problems simultaneously. The rocket booster has to separate from the upper stage at precisely the right moment and location to ensure that both vehicles end up where they're supposed to go. The booster then has to flip around, reignite its engines, and execute a powered descent back through the atmosphere to land on a target that might be moving at sea. The precision required for these booster landings is almost beyond belief. The rocket has to compensate for winds that change direction and strength throughout its descent. It has to account for engine performance variations and fuel consumption rates. It has to execute a complex series of maneuvers while traveling at speeds that would make a supersonic jet look sluggish. All of this happens automatically, controlled by computers that make thousands of calculations per second. But the software controlling these systems had to be written by humans who understood both the physics of rocket flight and the practical challenges of building machines that work reliably in extreme environments. The success of reusable rocket technology is opening up possibilities that seemed like science fiction just a few years ago. When the cost of reaching orbit drops dramatically, it becomes economically feasible to attempt projects that were never practical before. Large space stations, manufacturing facilities in orbit, even permanent settlements on other worlds start to look like engineering challenges rather than impossible dreams. But all of these future possibilities still depend on the same fundamental physics that have governed rocket flight since the beginning of the space age. Newton's laws of motion, the rocket equation, orbital mechanics. These principles remain as relevant today as they were when the first satellites were launched over 60 years ago. What's changed is our mastery of applying these principles. Our rockets are more reliable, more efficient, and more capable than ever before. Our understanding of orbital mechanics allows us to plan missions of incredible complexity and precision. Our materials science and manufacturing techniques allow us to build spacecraft that can operate for years or decades in the harsh environment of space. The journey from a rocket sitting on a launch pad to a spacecraft operating successfully in orbit represents one of humanity's greatest technical achievements. It requires mastering physics that operates on scales from the subatomic to the astronomical. It demands engineering precision that tolerates no errors and no second chances. It calls for human creativity and problem-solving skills that push the boundaries of what seems possible. And yet, for all its complexity, the basic story of how rockets reach space remains elegantly simple. We harness the power of controlled explosions to accelerate massive vehicles to incredible speeds. We use the predictable mathematics of orbital mechanics to navigate through space with precision that would have seemed magical to previous generations. We've learned to work with the fundamental forces of nature rather than against them, turning gravity from an enemy into an ally. This mastery of spaceflight represents more than just a technological achievement. It's a demonstration of what becomes possible when human curiosity meets rigorous scientific understanding. When we refuse to accept the limitations that seem to constrain us and instead ask how we might transcend them. The rockets climbing into the sky above us carry more than satellites and astronauts. They carry human dreams of exploration and discovery. They represent our species' determination to expand beyond the boundaries of our birth world and explore the vast cosmos that surrounds us. Every successful launch is a victory over the forces that would keep us earthbound. a proof that the impossible can become routine through careful application of scientific principles and engineering excellence. The moment a rocket finally achieves orbital velocity marks one of the most profound transitions in all of human experience. In the span of just 8.5 minutes, we've gone from being creatures bound to the surface of our planet to beings capable of existing in an environment that has no up or down, no ground beneath our feet, no atmosphere to breathe. We've entered a realm where the physics that govern every moment of our earthly existence simply no longer apply. But here's what's truly remarkable about this transition. The astronauts inside that spacecraft don't feel like they've conquered gravity. They feel like they're falling, and they are falling. Every single second of every single day they spend in orbit, they're plummeting toward Earth at exactly the same rate as their spacecraft. The only reason they don't hit the ground is that they're moving sideways so fast that Earth's surface curves away beneath them faster than they can fall toward it. This creates the strangest sensation imaginable. Imagine being in an elevator when the cable snaps. That feeling of weightlessness in your stomach as you begin to fall. That's exactly what astronauts experience constantly in orbit. Except instead of lasting for a terrifying few seconds before impact, it goes on for months. Their bodies, their equipment, even the water they drink, everything is in a constant state of free fall. This weightless environment creates challenges that most people never consider. How do you eat when your food floats away? How do you sleep when there's no up or down to orient yourself? How do you use the bathroom when gravity isn't there to help things go where they're supposed to go? These aren't just minor inconveniences. They're fundamental problems that had to be solved through years of experimentation and some very creative engineering. Water behaves completely differently in zero gravity. Instead of flowing in streams, it forms perfect spheres that float through the air like liquid marbles. These water spheres can be dangerous if they float into electronic equipment, or if an astronaut accidentally inhales one. The space station has special ventilation systems that constantly move air around to prevent water droplets from accumulating in dangerous places. Fire burns differently too. On Earth, hot gases rise because they're less dense than cool air, creating the familiar teardrop shape of flames. But in weightlessness, there's no up or down for hot gases to rise toward. Flames burn in perfect spheres, consuming oxygen more efficiently, but also more unpredictably. This makes fire one of the most serious threats aboard spacecraft, because flames can spread in ways that are impossible to predict based on earthbound experience. Even the human body struggles to adapt to this alien environment. Our cardiovascular system evolved to pump blood upward against gravity from our legs to our brain. In weightlessness, blood shifts toward the head, causing the puffy-faced appearance that astronauts develop after just a few days in space. The heart doesn't have to work as hard, so it begins to lose muscle mass. Bones start to weaken because they're no longer bearing the body's weight. These physiological changes aren't just temporary inconveniences. They represent fundamental alterations to how human biology functions. Astronauts who spend months in space return to Earth significantly weakened, requiring extensive rehabilitation to readapt to living in a gravitational environment. Some changes, like bone density loss, can take years to fully recover from. But the challenges of living in space extend far beyond the human body's adaptation to weightlessness. The space environment itself is actively hostile to both human life and mechanical systems. The vacuum of space doesn't just mean there's no air to breathe. It means that any liquid will instantly boil away. Any gas will expand explosively. and materials that are perfectly stable on Earth can suddenly become volatile and dangerous. Temperature swings in space are more extreme than anywhere on Earth. In direct sunlight, surfaces can heat up to over 300 degrees Fahrenheit. In the shadow of Earth, they can plummet to minus 250 degrees. These temperature changes happen rapidly as spacecraft move in and out of Earth's shadow every 90 minutes, causing constant thermal expansion and contraction that can crack materials or cause mechanical systems to fail. The radiation environment in space is unlike anything we experience on Earth's surface. Our planet's magnetic field and atmosphere protect us from most of the high-energy particles streaming from the sun and deep space. But spacecraft operating above the atmosphere are constantly bombarded by radiation that can damage electronics, degrade materials, and pose serious health risks to astronauts. Solar storms can be particularly dangerous, unleashing bursts of radiation intense enough to kill an unprotected human in minutes. During major solar events, astronauts aboard the space station have to take shelter in specially shielded compartments and wait for the storm to pass. Mission controllers on Earth constantly monitor space weather conditions, ready to issue warnings if dangerous radiation levels are detected. Micrometeoroids present another constant threat that most people never consider. Space might seem empty, but it's actually filled with tiny particles traveling at velocities that make bullets look sluggish. A fleck of paint traveling at orbital velocity hits with the kinetic energy of a small bomb. Larger debris can punch holes through spacecraft hulls or shatter windows designed to withstand tremendous pressure differences. The International Space Station has been hit by debris thousands of times during its decades in orbit. Most impacts are too small to cause serious damage, but the station's hull is constantly being peppered by particles that gradually wear away the outer surfaces. The station has special shielding designed to protect against debris impacts, but there's always the risk that a larger piece might get through. Space debris created by human activity has become an increasingly serious problem as more satellites are launched and more missions are conducted. Every rocket launch potentially creates debris. Every satellite that fails or reaches the end of its operational life becomes a hazard for other spacecraft. This debris can remain in orbit for decades or centuries, creating a growing cloud of hazardous material around our planet. The problem is self-reinforcing. When two pieces of debris collide, they create thousands of smaller fragments, each traveling at orbital velocity and capable of destroying other spacecraft. Scientists call this the Kessler syndrome, a cascade effect where collisions create more debris, which causes more collisions, potentially making certain orbital regions too dangerous to use. Managing these risks requires constant vigilance and sophisticated tracking systems. Ground-based radars and telescopes monitor thousands of objects in orbit, calculating their trajectories and predicting potential collisions. When debris is detected on a collision course with the space station or other critical spacecraft, mission controllers can order avoidance maneuvers to move out of harm's way. But avoidance maneuvers consume precious fuel and can disrupt scientific operations or mission timelines. Every debris avoidance maneuver represents a compromise between safety and mission effectiveness. Sometimes the risk calculations are so close that mission controllers have to make split-second decisions about whether to maneuver or accept the calculated risk of impact. These operational challenges highlight something that's often overlooked in discussions of space exploration. The technical achievement of reaching orbit is just the beginning of an ongoing battle for survival in an environment that's fundamentally hostile to both human life and human technology. Every day, That a spacecraft operates successfully in space represents a victory over forces that are constantly trying to destroy it. The life support systems that keep astronauts alive in this hostile environment are marvels of engineering in their own right. These systems have to provide breathable air, drinkable water, and a livable environment while operating with perfect reliability for months or years. There are no second chances in space. If the life support system fails, there's no calling for help, no backup plan except what you've brought with you. The air recycling systems aboard the space station are more sophisticated than anything that exists on Earth. They have to remove carbon dioxide exhaled by the crew, add fresh oxygen, control humidity levels, and filter out contaminants, all while operating in a weightless environment where normal convection doesn't work. The systems use a combination of chemical reactions, molecular sieves, and catalytic processes that would make a chemistry professor's head spin. Water recycling is even more critical and more challenging. Every drop of water aboard the space station is precious because launching water from Earth costs thousands of dollars per gallon. The station's water recovery systems can recycle virtually everything, including humidity condensed from the air and even urine from the crew. These systems are so efficient that the water they produce is actually purer than most municipal water supplies on Earth. But recycling systems can fail, and when they do, the consequences are immediate and potentially fatal. Astronauts have to be trained not just as scientists and pilots, but as repair technicians capable of troubleshooting and fixing complex systems under pressure. They work with tools designed specifically for weightless environments, often having to improvise repairs using whatever materials happen to be available. The psychological challenges of living in space are just as demanding as the technical ones. Astronauts are confined in a small space for months at a time, unable to go outside, unable to feel wind or rain or breathe fresh air. The view of Earth through the windows is spectacular, but it's also a constant reminder of how far they are from home, how isolated they are in the vast emptiness of space. The confined environment can create interpersonal tensions that would be manageable on Earth, but become serious problems when there's no way to get away from each other. Mission planners spend considerable effort selecting crew members who can work together effectively under stress. But personality conflicts can still develop during long-duration missions. Communication delays add another layer of psychological stress. While the space station is close enough to Earth that radio conversations can happen in real time, missions to Mars or the outer planets will involve communication delays of minutes or hours. Imagine trying to have a conversation with your family when every exchange takes 20 minutes or more. The isolation becomes not just physical, but temporal. These challenges explain why astronaut selection and training programs are so rigorous. It's not enough to be technically competent and physically fit. Astronauts have to demonstrate exceptional psychological resilience, the ability to remain calm and focused under extreme stress, and the interpersonal skills needed to work effectively in small teams under difficult conditions. The training programs simulate not just the technical aspects of spaceflight, but also the psychological stresses. Astronauts spend weeks in isolated environments, practicing emergency procedures while dealing with sleep deprivation, equipment failures, and interpersonal conflicts. They learn to function effectively when everything is going wrong, and there's no possibility of outside help. But perhaps the most profound challenge of space exploration isn't technical or psychological, it's philosophical. When you're floating in a spacecraft hundreds of miles above Earth, looking down at the planet that contains everything and everyone you've ever known, it changes your perspective on what it means to be human. Astronauts consistently report that seeing Earth from space fundamentally alters their worldview, giving them a sense of the planet's fragility and the interconnectedness of all life. This perspective shift, often called the overview effect, represents something unprecedented in human experience. For the first time in our species' history, We have human beings who can look back at Earth from the outside, who can see our planet as a single, unified system floating in the cosmic void. This external perspective on our own world has profound implications for how we understand our place in the universe. The images and videos that astronauts capture from space have become some of the most powerful tools for environmental awareness and global consciousness. When you see Earth from space, national borders disappear. The atmosphere appears as a thin, fragile shell protecting all life from the hostility of space. The planet looks small, precious, and incredibly vulnerable. This shift in perspective has practical implications for space mission planning and design. Astronauts who have experienced the overview effect often become passionate advocates for space exploration, not because they want to escape Earth, but because they understand how space-based perspectives can help us better understand and protect our home planet. Earth observation from space has revolutionized our understanding of global climate systems, weather patterns, and environmental changes. Satellites can monitor deforestation, track pollution, measure ice cap thickness, and observe atmospheric chemistry in ways that are impossible from ground-based observations. The data collected from space has become essential for understanding and addressing environmental challenges on Earth. But space-based Earth observation also reveals the incredible complexity of the systems that make life on our planet possible. The delicate balance of atmospheric chemistry, ocean currents, and biological processes that maintain Earth's habitability becomes visible from the external perspective that space provides. This understanding makes clear just how remarkable it is that such a system exists at all, and how important it is to preserve it. The technological capabilities we've developed for space exploration are increasingly being applied to challenges on Earth. The life support systems designed for spacecraft are being adapted for underwater habitats and extreme environment research stations. The materials science developed for rockets and spacecraft is finding applications in everything from automotive manufacturing to medical devices. Solar panels, originally developed for satellites, have become one of the most important renewable energy technologies on Earth. The miniaturization techniques used in spacecraft electronics have driven advances in consumer electronics. Even the freeze-dried foods developed for astronauts have found their way into grocery stores and emergency preparedness supplies. But perhaps the most important technology transfer from space exploration is the systems thinking approach that's necessary for designing spacecraft and missions. When you're building a machine that has to work perfectly in an environment where there's no possibility of repair or replacement, you develop a mindset that considers every possible failure mode and designs redundancy into every critical system. This approach to engineering has applications far beyond spacecraft design. It's being applied to power grid management, hospital life support systems, and other critical infrastructure where failure isn't an option. The rigorous testing and quality control procedures developed for space missions are being adapted for manufacturing processes that demand extreme reliability. The commercial space industry that has emerged in recent decades is beginning to make space access routine rather than extraordinary. Companies are developing rockets that can fly multiple missions, reducing the cost of reaching orbit by orders of magnitude. This economic transformation is opening up possibilities that were never feasible when every space mission required building custom hardware from scratch. Satellite constellations with thousands of spacecraft are becoming economically viable, providing global internet coverage and Earth monitoring capabilities that would have been prohibitively expensive with traditional space technology. Space manufacturing is beginning to look realistic for products that benefit from the weightless environment or the extreme vacuum of space. Space tourism is transitioning from fantasy to reality, with companies offering suborbital flights that give passengers a few minutes of weightlessness and a view of Earth from space. While these flights don't achieve the orbital velocities needed to stay in space, they provide a taste of the space experience and help build the infrastructure and experience needed for more ambitious civilian space activities. The reusability revolution in rocket technology is perhaps the most significant development in space transportation since the invention of the rocket itself. When rocket boosters can land back on Earth and be refurbished for multiple flights, the economics of space access change fundamentally. Instead of throwing away millions of dollars worth of hardware with every launch, the same rocket can fly dozens of times. This reusability doesn't just reduce costs, it also enables rapid iteration and improvement of rocket designs. When you're building rockets that fly only once, every design change takes years to implement and test. But when the same rocket flies repeatedly, you can make incremental improvements and test them quickly, leading to rapid advances in performance and reliability. The precision required for rocket reusability is almost beyond belief. A rocket booster has to separate from the upper stage at exactly the right moment and location, flip around in mid-flight, reignite engines that have been shut down for several minutes, and execute a controlled descent through the atmosphere to land on a target that might be moving at sea. The guidance systems that make this possible represent some of the most sophisticated control software ever written. These systems have to account for engine performance variations, atmospheric conditions, fuel consumption rates, and dozens of other variables while making thousands of calculations per second. The margin for error is essentially zero because a failed landing destroys the entire vehicle. The success of reusable rocket technology is enabling mission architectures that would have been impossible with traditional expendable rockets. When launch costs drop dramatically, it becomes feasible to send much larger payloads to space or to conduct missions that require multiple launches. This is opening up possibilities for large-scale space construction, permanent lunar bases, and even Mars colonization missions. But reusability also creates new challenges for mission planning and operations. Reusable rockets have to be inspected, refurbished, and tested between flights, which takes time and resources. The turnaround time between flights becomes a critical factor in mission scheduling. The reliability of reused hardware has to be demonstrated through extensive testing and operational experience. The integration of reusable rockets with traditional space mission operations requires new approaches to everything from payload integration to launch scheduling. Mission planners have to consider not just whether a rocket can deliver their payload to the desired orbit, but also how the reusability requirements affect the mission timeline and cost structure. These operational changes are rippling through the entire space industry, affecting everything from satellite design to mission insurance. When space access becomes more routine and predictable, it changes the risk calculations for space-based businesses and enables new types of commercial activities that wouldn't have been viable with traditional space transportation costs. The democratization of space access is also changing who gets to participate in space exploration. University research groups can now afford to build and launch their own satellites. Developing nations can access space-based services without having to develop their own space programs. Small companies can experiment with space-based manufacturing or services that would have required government-level resources just a few decades ago. This expansion of space access is creating a positive feedback loop, where more activity in space drives down costs further, which enables even more activity. The result is an accelerating expansion of human presence and capability in space that's happening faster than most people realize. But with this expansion comes new responsibilities and challenges. As space becomes more crowded and commercialized, we need new approaches to space traffic management, orbital debris mitigation, and international cooperation in space. The legal and regulatory frameworks that govern space activities are struggling to keep up with the pace of technological change. The environmental impact of increased space activity is also becoming a concern. Rocket launches release pollutants into the atmosphere, and the growing number of satellites in orbit is beginning to affect astronomical observations from Earth. The space debris problem is getting worse as more objects are launched, creating long-term sustainability challenges for space activities. These challenges require international cooperation and forward-thinking policy decisions. Space is a global commons that affects everyone on Earth, but it's governed by a patchwork of national laws and international treaties that were written decades ago when space access was limited to a few government programs. The solutions to these challenges will likely require the same kind of systems thinking and engineering approach that makes spacecraft work reliably in the first place. We need to design space activities for long-term sustainability, just as we design spacecraft for long-term operation in hostile environments. The future of space exploration will likely involve a combination of government programs pushing the boundaries of what's possible and commercial companies making space access routine and affordable. This partnership between public and private sectors is already driving innovations that neither could achieve alone. Government space agencies bring the resources and long-term perspective needed for ambitious exploration missions that might not have immediate commercial applications. Commercial companies bring the efficiency and rapid iteration capabilities that can drive down costs and improve reliability. Together, they're creating capabilities that seem like science fiction just a few years ago. The next phase of space exploration will likely focus on establishing permanent human presence beyond Earth orbit, lunar bases that can support crews for months or years, Mars missions that don't just visit but establish ongoing research stations, asteroid mining operations that can provide resources for further space development. These ambitious goals will require solving challenges that make current space missions look simple by comparison. Long-duration life support systems that can operate for years without resupply from Earth, radiation shielding that can protect crews during interplanetary voyages, in-space manufacturing capabilities that can produce tools and equipment from raw materials found in space. But the fundamental principles that enable all of these future possibilities remain the same ones that power every rocket launch today. Newton's laws of motion, the rocket equation, orbital mechanics, thermodynamics, materials science, and systems engineering. The physics hasn't changed, but our mastery of applying these principles continues to advance at an accelerating pace. The story of how rockets work is ultimately the story of how human beings learn to transcend the limitations that seem to define our existence. We looked at the vast emptiness above our heads and refused to accept that it was forever beyond our reach. We studied the fundamental forces of nature and found ways to harness them for purposes they were never intended to serve. Every rocket that climbs into the sky represents a victory over the forces that would keep us earthbound. Every successful mission to space demonstrates that the impossible can become routine through the patient application of scientific principles and engineering excellence. Every astronaut who looks back at Earth from orbit gains a perspective on our planet and our place in the universe that would have been unimaginable to previous generations. The rockets thundering off launch pads around the world are carrying more than satellites and supplies and human passengers. They're carrying human dreams of exploration and discovery into the cosmic void. They represent our species' refusal to be confined by the accident of our birth on the surface of one small planet orbiting an ordinary star. In learning to build machines that can escape Earth's gravitational embrace, we've discovered something profound about the nature of human potential. We've learned that the boundaries that seem to constrain us are often self-imposed. that the impossible is frequently just the untried, and that the universe is not a place that excludes us, but a realm that invites our exploration. The gentle art of controlled falling that we call orbital mechanics has taught us to work with natural forces rather than against them. The precise choreography required to launch rockets successfully has shown us that complexity can be mastered through careful analysis and systematic preparation. The hostile environment of space has demonstrated that human ingenuity can create islands of habitability in the most unlikely places. These lessons extend far beyond the technical domain of rocket science and space exploration. They speak to fundamental questions about human nature and human potential. They suggest that our capacity for understanding and transcending our limitations may be far greater than we typically imagine. As we stand on the threshold of becoming a truly spacefaring civilization, we carry with us all the hard-won knowledge and experience that has brought us this far. The physics of rocket propulsion, the mathematics of orbital mechanics, the engineering principles that make spacecraft reliable, the operational procedures that keep astronauts safe and missions successful. But we also carry something equally important and perhaps more precious: the sense of wonder and curiosity that drives us to ask impossible questions and then spend decades figuring out how to answer them. The conviction that exploration and discovery are not luxury activities but essential expressions of what it means to be human. The understanding that in reaching for the stars, we don't diminish our connection to Earth, but rather gain the perspective needed to truly appreciate the remarkable planet that gave us birth. The numbers behind this achievement are staggering in ways that most people never consider. When that rocket finally shuts down its engines and coasts into the silence of orbital velocity, it has consumed fuel at rates that would empty entire lakes. The Saturn V that carried astronauts to the moon burned through fuel so fast that in the time it takes you to read this sentence, it would have consumed more fuel than most cars use in an entire year. But fuel consumption is just the beginning of understanding the sheer scale of what we've accomplished. The precision required to hit orbital velocity is like trying to throw a baseball from New York to Los Angeles and having it land in a teacup. Except the baseball is traveling at 17,000 miles per hour. The teacup is also moving at 17,000 miles per hour, and you only get one shot to make it work. This precision emerges from decades of accumulated knowledge about how objects move in the gravitational fields of celestial bodies. Every successful orbital insertion builds on lessons learned from thousands of previous missions, each one teaching us something new about the subtle forces that govern motion in space. The computers controlling modern rockets process more information in a single second than mission controllers had access to during the entire Apollo program. They're constantly adjusting engine thrust, monitoring structural loads, tracking trajectory deviations, and preparing for contingencies that might occur milliseconds in the future. The software running these systems represents millions of lines of code that have been tested and retested under every conceivable scenario. Yet despite all this computational power, the fundamental challenge remains exactly the same as it was for the first rockets launched decades ago. You're trying to accelerate a massive object to incredible speeds while fighting against forces that want to tear it apart or drag it back to Earth. The tools have gotten more sophisticated, but the physics remains unchanged. The moment of engine cutoff marks one of the most profound transitions in all of human experience. In the span of a few seconds, the violent shaking and thunderous noise of powered flight gives way to the absolute silence of orbital mechanics. The crushing acceleration that pressed astronauts into their seats suddenly vanishes, replaced by the strange sensation of weightlessness. This transition isn't gradual. It happens instantly when the engines shut down. One moment, you're being pushed by millions of pounds of thrust. The next moment, you're falling freely through space at orbital velocity. The contrast is so dramatic that astronauts often describe it as the most startling moment of their entire space experience. But reaching orbit is just the first step in a journey that might last for months or years. The spacecraft that emerges from those 8.5 minutes of powered flight has to operate reliably in an environment that's fundamentally hostile to both human life and mechanical systems. Every component, every system, every line of software code has to work perfectly because there's no possibility of calling for help or pulling over to make repairs. The redundancy built into spacecraft systems would seem excessive for any Earthbound application. Critical systems often have 3 or 4 backups, each one capable of taking over if the primary system fails. Life support systems are designed to continue operating even if multiple components fail simultaneously. Navigation systems can determine position and velocity using completely different methods if the primary sensors are damaged. This redundancy comes at a tremendous cost in weight and complexity. Every backup system adds mass that has to be accelerated to orbital velocity. Every redundant component increases the chances that something, somewhere, might malfunction. Spacecraft designers have to balance the need for reliability against the fundamental constraint that every additional pound makes the mission more difficult and expensive. The solutions they've developed represent some of the most elegant engineering compromises ever achieved. Systems that can operate in multiple modes depending on which components are working. Software that can reconfigure itself automatically when hardware fails. Structures that can continue functioning even when damaged by micrometeorite impacts or thermal stress. The material science that makes these solutions possible pushes the boundaries of what's achievable with current technology. Spacecraft use alloys that remain strong at temperatures that would melt steel, composites that are lighter than aluminum but stronger than titanium, and electronic components that can function reliably while being bombarded by radiation that would be lethal to unprotected humans. These advanced materials don't just happen. They're the result of decades of research and development, often driven by the extreme requirements of space applications. The technologies developed for spacecraft often find their way into terrestrial applications, but the space environment provides unique challenges that drive innovations that wouldn't emerge from Earthbound needs alone. The thermal management systems aboard spacecraft represent perhaps the most sophisticated temperature control technology ever developed. These systems have to maintain precise temperatures for sensitive electronic components, while the outside of the spacecraft swings between extremes that would destroy most materials. They use heat pipes, radiators, and phase-change materials in configurations that seem to defy the laws of thermodynamics. Power generation in space presents its own unique challenges. Solar panels work beautifully in the unfiltered sunlight above Earth's atmosphere, but they have to be designed to handle temperature swings, radiation exposure, and micrometeorite impacts that would quickly destroy terrestrial solar installations. The efficiency of space-qualified solar panels often exceeds that of ground-based systems, but they cost hundreds of times more per watt. Battery systems for spacecraft have to operate reliably for years while cycling through charge and discharge cycles that would kill conventional batteries in weeks. They have to function in vacuum, survive launch vibrations, and provide consistent power output across temperature ranges that span hundreds of degrees. The combination of all these systems creates spacecraft that are marvels of engineering integration. Every subsystem has to work harmoniously with every other subsystem while operating in conditions that exist nowhere else in human experience. The testing required to verify that these integrated systems will work reliably takes years and costs millions of dollars. Ground testing can simulate many aspects of the space environment, but it's impossible to perfectly replicate the combination of vacuum, radiation, temperature extremes, and weightlessness that spacecraft encounter in orbit. This means that every space mission is, to some extent, an experiment in whether the engineering predictions will hold up under real operating conditions. The success rate of modern space missions is testimony to how well engineers have learned to design for this unforgiving environment. But every mission also teaches new lessons about the subtle ways that space can challenge even the most carefully designed systems. These lessons feed back into the design process for future missions, creating a continuous cycle of learning and improvement. The operational lifetime of spacecraft often exceeds their design specifications by factors of 2, 3, or even 10. The Voyager probes, launched in 1977, are still transmitting data after more than 4 decades in space. The Opportunity rover on Mars operated for 14 years despite being designed for a 90-day mission. These extended lifetimes aren't accidents. They result from conservative design practices and robust engineering that builds in substantial safety margins. But extended missions also create new challenges for mission operations teams. Spacecraft that were expected to operate for a few years suddenly need support for decades. Components begin to fail in ways that weren't anticipated during the original design process. Mission controllers have to become creative problem solvers, finding ways to work around failed systems and extract useful science from degraded capabilities. The psychological impact on mission teams during these extended operations is profound. Engineers and scientists who were young when a mission launched might be approaching retirement by the time it ends. They develop deep emotional attachments to spacecraft that they've guided through decades of discoveries and challenges. The end of a long-duration mission is often as much a personal loss as a scientific conclusion. This human element of space exploration often gets overlooked in discussions of rockets and orbital mechanics. But behind every successful mission are teams of dedicated professionals who spend years or decades of their careers nurturing these mechanical explorers. They celebrate each successful maneuver, worry through every anomaly, and mourn when missions finally come to an end. The knowledge and experience gained from these long-duration missions is now being applied to even more ambitious projects. Missions to the outer planets that will take decades to reach their destinations. Interstellar probes that will operate for centuries as they journey to nearby star systems. Mars sample return missions that require unprecedented coordination between multiple spacecraft across millions of miles. These future missions will push every aspect of spacecraft design and operations to new limits. They'll require propulsion systems that can operate reliably for decades, communication systems that can maintain contact across interstellar distances, and autonomous systems that can make complex decisions without human guidance. The technologies being developed for these missions will likely revolutionize space exploration in ways we can barely imagine. But they'll all build on the same fundamental principles that govern every rocket launch today: the physics of propulsion, the mathematics of orbital mechanics, the engineering principles that make reliable spacecraft possible. The story of how we learn to escape Earth's gravitational embrace and operate in the hostile environment of space is ultimately a story about human persistence and ingenuity. We refuse to accept the limitations that seem to confine us to the surface of our planet. We studied the fundamental forces of nature until we understood them well enough to harness them for our purposes. Every rocket that successfully reaches orbit represents a victory over forces that are billions of years older and vastly more powerful than human civilization. Every spacecraft that operates successfully in space demonstrates our growing mastery of an environment that was never intended to support human activity or human-built machines. The precision, reliability, and sheer audacity required to make all of this work continues to push the boundaries of what's possible with current technology and current understanding. Each mission teaches us something new about the challenges and opportunities that await us as we expand our presence beyond Earth. The future of space exploration will likely involve missions and capabilities that seem impossible from our current perspective, just as today's routine space operations would have seemed miraculous to the pioneers of rocket science. But whatever form that future takes, it will be built on the foundation of knowledge and experience we are accumulating with every launch, every orbit, every successful mission to the void beyond our atmosphere. We stand at a remarkable moment in human history when the dream of becoming a spacefaring civilization is transitioning from fantasy to engineering challenge. The rockets climbing skyward from launch pads around the world are carrying us toward a future where human presence in space becomes permanent, sustainable, and eventually routine. That future will bring challenges we haven't yet imagined and opportunities we can barely conceive. But it will be achieved through the same combination of scientific understanding, engineering excellence, and human determination that makes every rocket launch a small miracle of controlled violence and precision timing. In the end, the story of how rockets reach space is really the story of how human beings learn to transcend the most basic constraints of our existence. We looked up at the infinite darkness above our heads and decided it wasn't a barrier, but a destination. We turned the hostile void of space from an enemy into a frontier. And we continue to push further into that frontier with every thunderous launch that tears through the sky above us. Tonight, as you drift off to sleep, remember that above your head, dozens of spacecraft are silently gliding through the cosmic void, following trajectories planned years ago, carrying out missions that will expand human knowledge for generations to come. They are our mechanical ambassadors to the infinite darkness, each one a testament to humanity's refusal to accept the boundaries that gravity tried to impose upon us. The next time you see a rocket launch, whether it's a routine cargo mission or a crew heading to the space station, you'll understand that you're witnessing something far more profound than just a machine climbing into the sky. You're watching humanity's greatest magic trick, the art of turning controlled explosions into controlled flight, of transforming the fundamental forces that bind us to Earth into the very mechanism of our escape. You're seeing physics and chemistry and mathematics and human ingenuity all working together in perfect harmony for just 8.5 minutes to accomplish something that defies every instinct we've developed over millions of years of evolution. You're watching matter become motion, watching potential energy transform into kinetic energy, watching Newton's laws play out on a scale that would make the great physicist himself weep with wonder. But more than that, you're witnessing the physical manifestation of human curiosity and determination. Every rocket that climbs towards space carries within its metal frame the accumulated dreams and knowledge of countless generations who looked up at the night sky and wondered what lay beyond. From ancient astronomers who map the movements of planets to modern engineers who calculate orbital mechanics, each launch represents the collective wisdom of our species, focused on a single, audacious goal. The thunderous roar that rattles windows for miles around a launch pad isn't just the sound of burning fuel and expanding gases. It's the sound of human limitations being shattered, of boundaries being crossed, of the impossible becoming routine through the patient application of scientific principles and engineering excellence. And in those moments when the engines finally cut off and silence fills the spacecraft, when the crushing weight of acceleration gives way to the strange dance of orbital mechanics, something magical happens. Humanity takes another step beyond the world that gave us birth, extending our reach into the cosmos itself. The precision required for all of this to work is so extraordinary that it seems to mock the chaos and uncertainty that characterizes so much of human experience. While we struggle to predict tomorrow's weather or manage the complexities of earthbound life, we can calculate exactly where a spacecraft will be in its orbit months or years in advance. We can predict with mathematical certainty that two objects traveling at 17,000 miles per hour will meet at precisely the right moment in the vast emptiness of space. This mastery of orbital mechanics represents one of humanity's greatest intellectual achievements. We've learned to read the invisible sheet music of gravitational forces, conducting symphonies of motion that span years and traverse billions of miles. We've turned the apparently chaotic dance of celestial bodies into a predictable highway system that our spacecraft navigate with precision that would make a Swiss watchmaker jealous. But perhaps the most remarkable aspect of this entire endeavor is how it reveals the deep interconnectedness between the cosmic and the personal. The same physical laws that govern the motion of galaxies also determine whether a rocket can escape Earth's gravitational well. The same mathematical principles that describe the behavior of subatomic particles also predict the trajectories of spacecraft bound for distant worlds. In learning to build machines that can climb out of Earth's gravity well, we've discovered something profound about the nature of the universe itself. We've found that reality operates according to elegant mathematical relationships that span scales from the infinitesimally small to the incomprehensibly vast. We've learned that the cosmos isn't a collection of separate, unrelated phenomena, but a single, unified system where everything influences everything else. This understanding has changed not just how we explore space, but how we see ourselves and our place in the grand scheme of existence. We are not separate from the universe we explore. We are part of it, temporary arrangements of stellar material that have somehow learned to contemplate their own cosmic origins. The carbon in our bodies was forged in the nuclear furnaces of ancient stars. The oxygen we breathe was created in stellar explosions that scattered heavy elements across interstellar space. The iron in our blood was manufactured in the final moments of dying suns. We are quite literally made of star stuff, cosmic debris that has organized itself into patterns complex enough to build rockets and wonder about the nature of existence. When we launch spacecraft into the void, we're not sending foreign objects into an alien realm. We're sending pieces of the cosmos back to explore other pieces of the cosmos. We're participating in the universe's ongoing project of understanding itself through the emergence of consciousness and curiosity. The rockets that pierce the sky above us carry more than scientific instruments and human passengers. They carry human consciousness itself into realms where it has never existed before. They extend the reach of awareness and wonder beyond the boundaries of our birth world, creating islands of human experience in the vast ocean of space. Every successful mission adds another chapter to the greatest story ever told, the story of matter becoming conscious of itself and reaching out to explore its own cosmic context. Every spacecraft that operates successfully in the hostile environment of space demonstrates that intelligence and determination can overcome forces that seem insurmountable. As you close your eyes and drift towards sleep, you can take comfort in knowing that you are part of this magnificent story. You are connected through physics and chemistry and cosmic evolution to every spacecraft currently gliding through the void above. The same atoms that form your thoughts were once part of ancient stars. The same forces that guide orbital mechanics also govern the biochemical processes that sustain your life. The rockets that thunder off launch pads around the world are carrying pieces of humanity's soul into the cosmic darkness, extending our presence into realms that seemed forever beyond our reach just decades ago. They represent our species' refusal to be confined by the accident of our birth on one small world orbiting an ordinary star. In mastering the art of controlled falling that we call orbital mechanics, we've learned something essential about the nature of human potential. We've discovered that the boundaries that seem to constrain us are often self-imposed, that the impossible is frequently just the untried, and that patient application of scientific principles can overcome obstacles that appear insurmountable. The gentle dance of spacecraft through the gravitational fields of planets and moons teaches us that power isn't always about force. Sometimes the most elegant solutions work with natural systems rather than against them, using the existing structure of reality as a framework for achievement rather than an obstacle to overcome. This lesson extends far beyond the technical realm of rocket science and space exploration. It speaks to fundamental truths about how progress happens, how challenges are overcome, how the seemingly impossible becomes routine through careful study, creative thinking, and persistent effort. Tonight, as you rest beneath the same sky that has inspired countless generations of dreamers and explorers, remember that you are living at a remarkable moment in human history. You are witnessing the transition from a single planet species to a civilization that spans multiple worlds. You are part of the first generation that has learned to escape the gravitational embrace of our birth planet and establish permanent outposts in space. The spacecraft currently orbiting overhead, the missions being planned for Mars and the outer planets, the technologies being developed for interstellar travel, all of these represent humanity's growing mastery of the cosmic environment. We are learning to thrive in the vast emptiness between worlds, turning the hostile void of space from a barrier into a highway. The future will bring challenges and opportunities that we can barely imagine. Permanent settlements on other worlds, manufacturing facilities that take advantage of weightlessness and vacuum, mining operations on asteroids rich with rare elements, perhaps even the first tentative steps toward other star systems. But whatever form that future takes, it will be built on the foundation we're laying today with every successful rocket launch, every operational spacecraft, every lesson learned about surviving and thriving in the space environment. We are the pioneers of a new age of exploration, the first generation to take seriously the possibility of becoming a truly cosmic civilization. The rockets climbing skyward above us are more than technological marvels. They are symbols of human aspiration, monuments to our refusal to accept limitations, proof that curiosity and determination can overcome forces billions of years older and vastly more powerful than human civilization itself. Sweet dreams, fellow traveler in the cosmic dance. The universe continues its ancient symphony around you, and you are part of that music now and always. May your rest be filled with wonder at the magnificent reality we call home. And may you wake tomorrow with renewed appreciation for the remarkable achievement that allows machines built by human hands to dance among the stars. I wish you a very good night. Hope you had an amazing time with me here, and you didn't drift off midway, or you did. Anyways, this is Boring Science signing off. Cheers.